Right now, a galaxy is being torn apart just above the Milky Way's disk. It is not 2.5 million light-years away. It is not Andromeda. It sits barely 70,000 light-years from Earth, and its stars are already mixing with ours in slow motion. This is one of the truly closest galaxies to us, and even it lies farther than any human machine has ever even come close to crossing. When people say Andromeda is our nearest galactic neighbour, they are quietly ignoring dozens of smaller galactic worlds hiding much nearer to home. And when we do the math on reaching any of them, the numbers turn from ambitious to absurd. Because getting there would require humanity itself to become something entirely new before it ever arrived. If this kind of deep exploration is something that fascinates you, consider tapping like and subscribe. It genuinely helps this channel keep making journeys like this one. Now, settle in. Get yourself comfortable. Let's begin. Open any introductory astronomy book, click on any beginner-friendly space article, watch any casual documentary about the cosmos, and sooner or later, you will meet the same sentence. Andromeda is our nearest galactic neighbour. It is offered as a simple, almost cozy fact. A single spiral of stars floating 2.5 million light-years away, waiting across the dark for humanity to notice it. The sentence sounds clean. It sounds settled. It sounds like something you can memorize once and forget forever. The sentence is wrong. Not almost wrong. Not technically wrong. Not wrong in some picky, footnoted way that only professional astronomers care about. Wrong in the ordinary, straightforward sense that it hides dozens of galaxies sitting much closer to us than Andromeda ever has, and that it has been quietly hiding them for as long as most of us have been alive. There are galaxies whose stars are threaded through the Milky Way itself right now, being pulled apart in slow motion above and below the disk. There are galaxies orbiting us so faintly that we only discovered them within the last 2 decades. There are galaxies so intimately tangled with our own gravitational field that some astronomers argue about whether they still count as separate galaxies at all, or whether they have already been swallowed and are simply taking a long time to disappear. And once you understand that landscape, once you see the Milky Way as it actually is not a single spiral drifting alone in a quiet cosmic pond, but a large predator surrounded by a swarm of smaller companions, the friendly textbook sentence collapses. Andromeda is not our nearest galactic neighbour. Andromeda is our nearest major galactic neighbour. Those 2 words in the middle change everything. They change what the closest galaxy actually is. They change what a journey to it would look like. And they change the entire question we are asking, because how far is the closest galaxy turns out to depend, in the most uncomfortable way, on what we are willing to count as a galaxy in the first place. So before we can talk about how far away the closest one is, we have to do something that sounds trivial but is not. We have to define the word. And in doing that, we start to see why the phrase closest galaxy is one of the most misleading phrases in popular astronomy. A galaxy, in the most careful modern sense, is a gravitationally bound system of stars, gas, dust, and dark matter, held together by its own mass. That definition sounds like a formality, but hidden inside it are 2 arguments that professional astronomers still have. The first argument is about dark matter. A true galaxy, most researchers now agree, sits inside its own halo of dark matter, its own private gravitational cocoon. That distinguishes it from a globular star cluster, which is just a dense ball of stars with no meaningful dark matter around it. The second argument is about independence. To count as a galaxy in the fullest sense, a system is usually expected to have formed on its own, evolved on its own, and been recognizably its own object before some larger galaxy came along and started eating it. That second condition is the one that quietly ruins the tidy sentence about Andromeda, because when you look carefully at the space immediately around the Milky Way, you do not see a peaceful gap between our galaxy and Andromeda. You see a crowd, a messy, still being cleaned up crowd of smaller stellar systems, some of them clearly galaxies, some of them clearly not, and some of them arguing about it in the middle. Most of these systems are what astronomers call dwarf galaxies. They are small, sometimes containing only a few thousand or a few million stars, compared to the roughly 100 billion to 400 billion stars in the Milky Way. They are faint, they are old, and they are close. Not close in the way Andromeda is close, close in a way that makes Andromeda look like it is in another postcode. Let us start with the one that best breaks the textbook sentence into pieces. Its name is the Sagittarius Dwarf spheroidal galaxy, and its story is quietly one of the most disturbing stories in modern galactic astronomy. It was only discovered in 1994, a whole galaxy on our doorstep, unnoticed until the last decade of the 20th century, because it lies almost directly on the far side of the galactic centre from us. Its stars are hidden behind the thick clouds of gas and dust that block our view toward the middle of the Milky Way. It took careful surveys of stellar motions to realise that a coherent, separate galactic system was sitting right there, tucked behind the glare of the core. But here is the part that matters for our question. The Sagittarius Dwarf is not a comfortable neighbour minding its own business. It is being destroyed, actively, right now. The Milky Way's enormous gravity is pulling it apart, stretching its stars into long trailing streams that wind around our entire galaxy multiple times, like ribbons unspooling from a torn parcel. The core of the Sagittarius Dwarf still exists, still faintly holding itself together, still recognizable as its own object. But its outer stars have already been stolen. They are drifting through the Milky Way's halo, mixing with our stars, becoming part of us. In a few 100 million more years, there will be nothing left to call the Sagittarius Dwarf. It will just be scattered material in the Milky Way's outer regions, a former galaxy digested into a current one. And it is close. Its centre lies approximately 70,000 light-years from Earth. That is closer than the far edge of our own Milky Way's disk. Understand that information. There is a galaxy whose core is nearer to us than parts of our own galaxy. The textbook sentence about Andromeda being our nearest galactic neighbour does not survive contact with the Sagittarius Dwarf. It cannot. 2.5 million light-years is more than 35 times farther than 70,000. The sentence is not slightly off. It is off by a factor that turns the whole map inside out. But here is the twist that makes it worse and more honest. The Sagittarius Dwarf is being absorbed. Depending on how strictly you define an independent galaxy, you might argue that it no longer counts as one. You might argue that we should not use a half-eaten galaxy as our answer to the question, what is the closest galaxy to the Milky Way? And that is a fair argument. But if you make it, you have to make it consistently. Because the moment you accept that a dying, dissolving companion no longer counts, you have to look at everything else nearby and ask the same question. And there is a lot else nearby. The Sagittarius Dwarf is not the first galaxy the Milky Way has been caught eating. It is only the most recent, the most visible, and the one whose consumption is still in progress. Careful analysis of stellar motions using data from the Gaia spacecraft, the European Space Agency's Precision Stellar Mapping mission, has revealed the ghostly outlines of an even older meal. Around 10 billion years ago, roughly 2/3 of the way back to the beginning of the universe, another galaxy fell into ours. Astronomers call it Gaia Enceladus, or sometimes the Gaia sausage, after the sausage-shaped pattern its stars trace in velocity space when plotted carefully. That galaxy was substantial, perhaps a quarter or a fifth of the size of the early Milky Way at the time of impact. It was not a small dwarf being nibbled at the edges. It was a genuine collision between comparable partners, and the Milky Way won. And the stars of Gaia Enceladus are still with us. They did not vanish. They did not scatter into intergalactic space. They mixed into what we now call the Milky Way's inner halo, and they can be identified today, 10 billion years later, by their distinctive orbits and their chemical fingerprints. A significant fraction of the older metal-poor stars in our galaxy's inner halo, including a number of stars visible from Earth on any clear night, are not native Milky Way stars at all. They were once citizens of another galaxy that our galaxy consumed before our sun even existed. This matters because it deepens the definitional problem we opened with. When we ask what the closest galaxy is, we are implicitly assuming that closest refers to something out there, some object that sits at a measurable distance from us. But galaxies leave residue. Long after they are absorbed, their stars remain, folded into the larger galaxy that ate them. In a strict sense, the closest galaxy to us right now includes the scattered remains of Gaia Enceladus, whose stars pass through the neighbourhood of the Sun in specific characteristic orbits. Those stars are, in origin, from another galaxy, and they are inside our own. There is, for instance, the Canis Major overdensity. This one is even more controversial than the Sagittarius Dwarf. It was reported in 2003 as a candidate dwarf galaxy, sitting only about 25,000 light-years from Earth, which would make it, if real, the closest galactic system to us that has ever been proposed. 25,000 light-years. That is closer than the distance from us to the Milky Way's own centre. And yet, in the years since, astronomers have argued vigorously about whether the Canis Major overdensity is actually a separate dwarf galaxy at all, or whether it is simply a natural warp and thickening of the Milky Way's own disk, mistaken for an external companion. Some studies support the galaxy interpretation, others reject it. The scientific status is genuinely unresolved, which itself is a fascinating lesson. We do not fully know what is orbiting us at close range. We are still, in the year we are living in, arguing about whether there is a dwarf galaxy hiding almost inside our own outer disk. Move outward slightly, and the crowd continues. There are Segue One and Segue Two, two of the faintest galaxies known anywhere. They are so dim, so sparse, so ghostly that they contain only a few hundred stars each that we can identify. For a long time, astronomers were not sure whether they were dwarf galaxies at all or simply unusual star clusters. Careful studies of their internal motions revealed that their stars are moving far too quickly for the visible mass alone to explain. Something invisible is holding them together. That is the fingerprint of dark matter. And by the working definition of a galaxy, a dark matter-dominated system with its own stars is a galaxy, no matter how faint. So, Segue One and Segue Two, sitting within about 70,000 to 135,000 light-years of us respectively, are among the smallest true galaxies we have ever found, and they too orbit closer than most people ever imagine. That question whether a system counts as a galaxy or merely as a dense star cluster is not a trivial one. It touches directly on what closest galaxy means. Consider Willman 1, discovered in 2005, which sits about 120,000 light-years from Earth. When it was first identified, astronomers could not decide what it was. It was too diffuse and too irregular to be a normal globular cluster. It was too small and too faint to look like a typical dwarf galaxy. For years, its classification bounced back and forth in the literature. The deciding test in each case was the same. If Willman 1's stars moved in a way that could be explained purely by the gravity of its visible mass, it was probably a star cluster. If its stars moved as if a much larger invisible mass were holding them together, it was a galaxy. Because a galaxy, in modern usage, is a system that requires dark matter to explain its motions. A star cluster is a system that does not. That distinction is what elevates Segue One from being merely an unusually sparse group of stars to being a full member of the Milky Way's galactic family. When astronomers measured the internal velocities of Segue One's stars carefully, they found stellar velocity dispersions far higher than the visible mass could account for. Segue One is dominated by dark matter, with ratios of several hundred to one. It is one of the most dark matter-dominated systems ever identified. This means that despite containing only a few hundred visible stars, it is unambiguously a galaxy in the modern technical sense. A vast, invisible gravitational cocoon holding a few sparse points of light together, drifting through the outskirts of our own galaxy. This is why the count of galaxies near us has kept climbing over the past 2 decades. It is not that new large systems keep appearing. It is that the definition itself has sharpened, and increasingly faint dark matter-dominated systems keep being confirmed as galaxies once their internal motions are measured with sufficient care. Then there is Antlia 2, discovered in 2019 using data from the European Space Agency's Gaia spacecraft. Antlia 2 is a strange one. It is enormous in physical size, roughly comparable in extent to the Large Magellanic Cloud, but it is astonishingly diffuse, so faint per unit area of sky that it hid from us for decades in plain view. It sits approximately 400,000 light-years away, farther than some of its cousins, but it is a reminder of something important. As recently as a few years ago, we were still finding entire galaxies sitting in our immediate cosmic neighborhood, invisible to us, until a spacecraft mapped the sky precisely enough to notice their sparse, drifting stars. When someone tells you, with confidence, that Andromeda is our nearest galactic neighbour, the honest response is that we are still discovering how many galactic neighbours we actually have. And once you start listing them, the list gets long fast. Ursa Major 2, Coma Berenices, Boots 1, Willman 1, whose galactic status is also debated, Draco, Ursa Minor, Sculptor, Sextans, Carina, Fornax, Leo 4, Leo 5, Hercules. Some of these are classical dwarf galaxies known for decades. Others are ultra-faint dwarfs, discovered only in the last 20 or so years through careful searches of survey data. Almost all of them sit within a few 100,000 light-years of us. Almost all of them are closer than Andromeda by factors of 10 to 50. And almost all of them are, in the strictest sense, gravitationally bound to the Milky Way. They are our satellites, our orbiting companions, our small siblings pulled along in our gravitational wake. Which brings us to a distinction that matters. Being a satellite of the Milky Way does not automatically mean you are not a galaxy. The Milky Way and Andromeda are both major galaxies of the local group, and both have their own retinues of satellite dwarfs. Andromeda's satellites include Messier 32 and Messier 110, along with many fainter dwarfs. Ours include everything we have been listing. A satellite galaxy is still a galaxy, in exactly the same way that a moon is still a real object. It just happens to be gravitationally bound to something larger. So, when we ask what the closest galaxy to the Milky Way is, the honest answer is that dozens of small galaxies are orbiting us right now, and most of them are far, far closer than Andromeda. The textbook sentence has been quietly counting only a certain kind of galaxy, the big, spectacular, spiral kind, and pretending the others do not exist. Now, some of you will already be asking the sensible question. If dwarf galaxies count, and the Sagittarius Dwarf counts, and the Canis Major overdensity might count, why do we keep hearing about Andromeda? The answer is that people are usually not asking what the closest galaxy is. They are asking, without quite realizing it, what the closest galaxy comparable to ours is. What the closest galaxy that looks like a proper spiral is. What the closest galaxy that lights up a beautiful photograph is. Andromeda answers that hidden question. It is the closest galaxy that resembles the Milky Way in size, in structure, and in visual grandeur. It is the closest galaxy that carries hundreds of billions of stars, a bright disk, a bulge, and a swirl of spiral arms. In that specific and much narrower sense, Andromeda genuinely is our nearest major galactic neighbour. But that is a different sentence. That is a careful, qualified, honest sentence. And it opens a different question, which is the question this episode is really about. Because once you accept the distinction between nearest galaxy of any kind and nearest major galaxy, you have to accept something else. There is no easy answer to what closest galaxy means. There are several answers, depending on what you count, and every one of those answers, even the friendliest, even the ones that let us pick the smallest, faintest, nearest dwarf orbiting us right now, is still a distance so far beyond human experience that we have almost no honest way to describe it. Let us make that concrete. The Sagittarius Dwarf's centre, at roughly 70,000 light-years, is closer to us than most of our galaxy's own stars. But 70,000 light-years is still 70,000 light-years. A single light-year is roughly 9.5 trillion kilometres. 70,000 light-years is nearly 700,000 trillion kilometres. Even if you were somehow moving at the speed of light itself, which nothing with mass can do, the trip to the centre of the Sagittarius Dwarf would take 70,000 years. Modern humans have existed as a distinct species for only a few 100,000 years. The trip to our closest dwarf galaxy, at the fastest speed physics allows, would consume a substantial fraction of the entire history of our kind of human, and that is the most forgiving answer available. That is the closest option on the menu. If you insist on independence, if you refuse to count the Sagittarius Dwarf because it is being absorbed, and you refuse to count Canis Major because its status is disputed, and you refuse to count the ultra-faint satellites because they are too small for your taste, the list of acceptable candidates thins quickly. You might end up with the Large Magellanic Cloud, orbiting us at about 163,000 light-years, or the Small Magellanic Cloud at close to 200,000 light-years, both visible to the naked eye from the southern hemisphere and both large enough to look like proper little galaxies of their own. These two are still gravitationally connected to the Milky Way. Modern measurements suggest they are on long, complicated orbits and may not have been our companions forever, but they are our companions now. They are the closest satellite galaxies that everyone agrees are galaxies, and even they, at those distances, are twice as far as the Sagittarius Dwarf center. There is a striking recent development on this front. For most of the 20th century, the Magellanic Clouds were assumed to be long-term satellites of the Milky Way, having orbited us for billions of years. That assumption survived, largely because nobody had a way to measure their motion precisely enough to test it. Then, in the 2000s, the Hubble Space Telescope and later the Gaia spacecraft produced measurements of the cloud's velocities that were dramatically more accurate than anything previous. The results surprised almost everyone in the field. The Large Magellanic Cloud is moving considerably faster relative to the Milky Way than a long-term companion should be moving. Its velocity is high enough that many researchers now favour a first infall model, in which the clouds are not ancient satellites at all, but relative newcomers, falling into the Milky Way for the first time, having only recently begun to be gravitationally captured by us. If that model is correct, and it is, at the time of this recording, the leading interpretation among the researchers who study these motions most closely, it means our second and third answers to what the closest galaxy is are galaxies that were, until quite recently in cosmic terms, independent members of the local universe. They may not be Milky Way satellites in the deepest sense at all. They may be interlopers, dwarfs that formed elsewhere and only recently arrived, which introduces yet another wrinkle into the definitional problem. Because the closest galaxy that is gravitationally bound to us turns out to be a shifting category. Systems come in, systems get absorbed, systems drift out, and the picture at any given moment depends on how careful your measurements are and how you interpret them. And if you insist on going even further, if you insist on the closest galaxy that is a proper independent giant, comparable in scale to the Milky Way itself, then and only then do you arrive at Andromeda at approximately 2.5 million light-years, which means the textbook sentence is not just wrong, it is the answer to a question no one thought to ask precisely. It is the answer to what is the closest galaxy that is basically like ours. It is not the answer to what is the closest galaxy. So the map we have to work with looks nothing like the popular picture. The popular picture shows the Milky Way, a comfortable stretch of empty space, then Andromeda. The real picture shows the Milky Way surrounded by a swarm of small, faint, sometimes dying, sometimes still forming, always intimate satellite galaxies. Some are being torn apart. Some are still being discovered. Some might not even be galaxies at all. And then, far beyond all of them, sits Andromeda, the nearest of the giants. There is a particular kind of vertigo that comes from realizing this, because our earlier sense of the closest galaxy was tied to a sense of separation. Andromeda felt like a destination, a distinct place, a somewhere else you could imagine pointing to and travelling toward. The real galactic neighbourhood does not have that clean separation. The Sagittarius Dwarf stars are already mixed into ours. The Canis Major structure, whatever it is, blurs into our own disk. The ultra-faint dwarfs orbit through the same halo of dark matter that we do. When you ask where the Milky Way ends, and where its nearest neighbour begins, the honest answer is that there is no clean line. Our galaxy has a fuzzy edge, and its nearest neighbours have fuzzy edges, and those edges overlap. That has an unsettling consequence for the whole project of visiting another galaxy. If the closest galaxy is one whose stars are already threaded through ours, what does it even mean to travel to it? Are we travelling to the Sagittarius Dwarf when we look up at certain streams of stars that pass through our own night sky? Are we already inside its remnants, in some sense? If so, has humanity, from a distance-only point of view, already crossed into another galaxy without noticing? And if the answer to that is uncomfortable, if the answer is that the Sagittarius Dwarf is too far gone to count, and the Canis Major structure is too uncertain to count, then we are back to the Magellanic Clouds, or to Andromeda, and the distances explode again. This is why the question this episode is asking cannot be answered with a single number. It is not how far is the closest galaxy. It is a series of nested questions. What counts as a galaxy? What counts as separate? What counts as reaching it? What counts as a human still being human when they arrive? Every layer of the question multiplies the difficulty, and the deeper we go, the more the friendly textbook sentence dissolves into something much stranger and much more honest. The Milky Way is not a lone spiral floating in a quiet pond. It is a giant surrounded by a scattered cloud of smaller companions, some of which are already inside it, some of which are about to be, and one of which, the largest, the most familiar, the most photogenic, is astonishingly far away, for what everyone calls our closest galaxy, which is where the real problem begins, because whichever definition you pick, whichever candidate you accept, the numbers are cruel. Even the friendliest, most generous answer to what the closest galaxy is places its center at a distance that a modern human spacecraft could not cross in 100 human civilizations laid end to end. Even light itself, the fastest thing that exists, would need tens of thousands of years to make the crossing. And that is before we even ask about the other galaxies. That is before we compare these distances to the width of the Milky Way, to the distance to the nearest star, to anything a human being can hold in their head. That comparison, when we do it properly, is what turns the friendly textbook sentence into something almost frightening. Because once you draw the real map, once you place the Sagittarius Dwarf and the Magellanic Clouds and Andromeda on a scale that a human body can understand, you discover that all the reassuring language about our galactic neighbours has been quietly relying on the fact that no one ever checks the ruler. On astronomical maps, these galaxies look adjacent to us. They look like dots pressed against the edge of our own dot. On a scale that matters for a spacecraft, or for a human lifetime, or for a civilization, they are not adjacent at all. They are catastrophically distant. And even our nearest, our smallest, our most half-eaten, our most quietly dissolving companion galaxy is still catastrophically distant. That is the real reveal hiding underneath the textbook sentence. Andromeda is not our nearest galactic neighbour. The Sagittarius Dwarf and Canis Major and Segue One and dozens of others are much nearer. And none of that helps. None of that shortens the trip to anything a human being could survive. None of that brings a galactic destination within reach. It only means that when we ask, how far is the closest galaxy, we get to pick which impossibly far number we would like to use. And now we are going to place those numbers on a real ruler. Not on a local group map where every galaxy is a friendly dot near every other dot. On a scale where the distance to the nearest star, the width of the Milky Way itself, and the gap to the Sagittarius Dwarf are drawn honestly next to each other. Because the moment those distances are laid out side by side, something breaks. The idea of a close galaxy stops meaning anything at all. There is a picture that appears whenever anyone talks about the local group of galaxies. You have seen it. It is on textbook pages, on educational posters, on the opening slides of astronomy lectures. It shows the Milky Way as a small labelled disk on one side of the frame, Andromeda as another labelled disk on the other side, a cluster of even smaller dots scattered around them, representing the various dwarf galaxies. A neat little arrangement, all of it fitting comfortably on a page. Sometimes there is a scale bar in the corner reading 1 million light years, or 500,000 light years, but almost nobody looks at the scale bar. What people take away from the picture is the emotional impression the picture creates. And the emotional impression is that these galaxies are neighbours, that they are close, that they belong together in the same visual frame the way houses on a street belong together in the same photograph. That impression is a trick, not a deliberate deception, but a trick nonetheless. When you compress hundreds of thousands or millions of light years onto a single page, everything on that page looks adjacent. The eye cannot help it. The eye evolved to interpret adjacency on the scale of things you might walk toward. It has no built-in defense against a scale bar in the corner that reads 1 million light years. So it treats the Sagittarius Dwarf as if it is right next to us, and the Large Magellanic Cloud as if it is basically touching us, and Andromeda as if it is just across the way. The map lies, not by including wrong information, by including truthful information, at a scale that makes the information feel wrong. So what we need to do next is redraw that map, not on a textbook page, but on a scale that a human body, a human spacecraft, and a human lifetime can actually measure themselves against. Because the moment the distances stop being crushed onto a page, everything changes. What looked like a friendly neighborhood in the local group picture turns into a landscape so vast that even the friendliest destinations we identified earlier become almost unreachable in principle. And the way we are going to feel that is by starting small. By starting, in fact, with the closest star. The nearest star system to the Sun is called Alpha Centauri. It is not one star but three, gravitationally bound together, a bright pair called Alpha Centauri A and B, and a small red companion called Proxima Centauri, which happens to be the actual closest single star to us. The whole system sits at a distance of about 4.37 light-years. That number gets quoted so often in so many articles about interstellar travel that it has almost lost its meaning. Let us restore some of the meaning. 4.37 light-years is roughly 41 trillion kilometers. If you tried to imagine that number on foot, or by car, or by any means of transport a human body has ever used, you would fail. A commercial jet flying non-stop toward Proxima Centauri, ignoring the small matter that it cannot fly through vacuum, would take approximately 5 million years to arrive. Voyager 1, the fastest spacecraft launched toward interstellar space, moves at about 17 kilometers per second. At that speed, pointed at Proxima Centauri, it would take roughly 75,000 years to arrive. 75,000 years. That is longer than the entire recorded history of human civilization applied to a trip toward the nearest star. And this is the important part. Alpha Centauri is not far by galactic standards. Alpha Centauri is next door. It is the closest possible destination in interstellar space. It is the answer to the question, what is the nearest thing outside our own solar system? And a Voyager speed journey to it takes something like 1,000 times longer than the entire history of writing. If Alpha Centauri, at 4.37 light-years, produces those numbers, imagine what happens when we start counting in thousands of light-years, or hundreds of thousands, or millions. So let us keep going. Let us step up one rung on this ladder. The next honest scale to place next to Alpha Centauri is not another star but our whole galaxy. The Milky Way is not a small object at Alpha Centauri scale. It is a colossal, sprawling structure whose full extent astronomers now think is far larger than the neat 100,000 light-years across figure that appeared in old textbooks. Modern observations of stellar streams and outer halo stars have pushed reasonable estimates of the Milky Way's true extent to something like 150,000 to 200,000 light-years, and possibly more, depending on where you decide to draw the edge. The bright, familiar spiral disk is only part of the story. Around it, a vast, diffuse halo of stars, dark matter, and captured debris extends out much, much further. Take the conservative number for the visible disk, roughly 100,000 light-years across, and compare it to Alpha Centauri. The nearest star is at 4.37 light-years. The Milky Way is over 20,000 times wider than that distance. If you shrank the trip to Alpha Centauri down to the length of your outstretched arm, the width of the Milky Way's disk would extend across a distance longer than several sports stadiums placed end to end. Alpha Centauri is a fingertip. The Milky Way is a landscape, and these are both objects we already live inside. That is worth pausing on. We do not have to leave the Milky Way to encounter distances that dwarf anything human machines have managed. Voyager 1, after nearly half a century of flight, has barely started to cross the outer edge of our Sun's influence, let alone made a dent in the distance to Alpha Centauri. And Alpha Centauri is a rounding error compared to the width of our own galaxy. Every one of the numbers we are about to use for other galaxies has to be understood in this context. We are not talking about scaling up from something we can nearly do. We are talking about scaling up from something we cannot even begin to do at interstellar scale. Now, bring in the Sagittarius Dwarf galaxy. We established earlier that its center lies at approximately 70,000 light-years from Earth. 70,000 light-years. That is close by galactic standards. Absurdly close for something officially labeled as a separate galaxy. In fact, it is closer to us than parts of our own Milky Way. But compare it to Alpha Centauri, 70,000 divided by 4.37 is roughly 16,000. The center of the Sagittarius Dwarf is about 16,000 times further from us than the nearest star. If Alpha Centauri is one step, the Sagittarius Dwarf is 16,000 steps in the same direction. And Alpha Centauri already required timescales longer than recorded human history for our fastest spacecraft to reach. 16,000 times that, just to reach the friendliest, most quietly dissolving, most half-eaten companion galaxy on the list. And now the picture starts to get uncomfortable. Because that number, 70,000 light-years, is not an accident of scale. It is roughly the width of the Milky Way's inner disk, which means, on a real ruler, the distance from Earth to the closest thing anyone calls a separate galaxy is comparable to the distance from Earth to the far side of our own galaxy. In other words, leaving the Milky Way and crossing the Milky Way are, at Sagittarius Dwarf distances, essentially the same kind of journey. Both are staggeringly long, neither is meaningfully shorter than the other. The word intergalactic and the word cross-galactic, when applied to a spacecraft, are not describing meaningfully different orders of magnitude at this scale. Let us push further out. The Large Magellanic Cloud, one of the two proper satellite galaxies visible with the naked eye from the southern hemisphere, sits at a distance of about 163,000 light-years. The Small Magellanic Cloud lies a little further out, near 200,000 light-years. These are the ones that most people, when pressed, will accept as genuine independent galaxies orbiting the Milky Way. They are large enough to see. They are structured enough to look like something. They are gravitationally bound to us, but distinct. Compare them to Alpha Centauri again. 163,000 divided by 4.37 is close to 37,000. The Large Magellanic Cloud is roughly 37,000 times farther than the nearest star. 200,000 divided by 4.37 is about 46,000. The Small Magellanic Cloud is roughly 46,000 times farther than the nearest star, and, once again, Alpha Centauri already broke every reasonable timescale for our fastest spacecraft. Multiply those timescales by 37,000, by 46,000, and the numbers stop being numbers. They become abstract labels for durations that no human institution has ever survived. Now, step to Andromeda, 2.5 million light-years approximately from Earth. In terms of Alpha Centauri, that is roughly 570,000 times further than the nearest star. In terms of Sagittarius Dwarf, that is roughly 36 times further than the closest dying satellite. In terms of the Large Magellanic Cloud, that is roughly 15 times further than our most familiar satellite galaxy. Andromeda is not merely a longer version of these trips. Andromeda is the moment where the scale changes character entirely. But here is the trap the local group map sets. When you look at the local group visualization, all of these, the Milky Way, the Sagittarius Dwarf, the Magellanic Clouds, Andromeda, appear as dots on the same picture. They look like they belong to the same visual category of close. The map does not lie about their positions, it only lies about their meaning. Because to a human body, and to a human spacecraft, the Sagittarius Dwarf and Andromeda are not both close. One is impossible on one timescale. The other is impossible on a timescale that is many times longer, moving in a direction that does not lie inside the Milky Way at all, but reaches across a stretch of intergalactic space that has almost nothing in it. Let us make this even more concrete with a fresh analogy. Imagine that you replace the distance to Alpha Centauri with the length of a single sheet of ordinary printer paper, about 30 centimeters. That sheet of paper stands for the nearest star. Now, on that scale, the width of the Milky Way's inner disk is approximately 23,000 sheets of paper laid end to end, a distance of roughly 7 kilometers. So the nearest star is a page in front of you. The width of our galaxy is an hour-long walk across town. On the same scale, the Sagittarius Dwarf center is around 5 kilometers from you. The Large Magellanic Cloud is about 11 kilometers from you. The Small Magellanic Cloud is around 13 or 14 kilometers from you. And Andromeda? Andromeda, on this same scale where Alpha Centauri is a single sheet of paper, sits approximately 170 kilometers away. 170 kilometers of that paper stretched out end to end. A full day of driving between us and our so-called nearest major galactic neighbor, when the nearest star has been reduced to something you can hold in one hand. That is what close means in the local group. That is the honest scale of the neighborhood. And even that image is being generous, because it lets you keep the intergalactic space clean and empty and easy to imagine. In reality, the space between the Milky Way and Andromeda is not really empty in a boring sense. It has been mapped, especially by observations over the last 2 decades, as an extended halo of hot, thin gas, stray stars, dark matter, and slow filaments of material. Some of it belongs to us. Some belongs to Andromeda. Some might belong to both, depending on how you draw the halos. When you look at recent modelling of the extended dark matter halos of both galaxies, some estimates suggest the 2 halos may already be technically touching, or nearly so, spanning a large fraction of the gap between us. But the visible stellar bodies, the parts you or I would ever describe as the galaxy itself, are separated by that full 2.5 million light-years of almost nothing. Now this is where the honesty of the map really cuts, because the local group picture treats all these distances as if they matter equally. On a page, Sagittarius Dwarf is a small hop, the Magellanic Clouds are a slightly larger hop, and Andromeda is a longer hop. That is misleading, because the actual leaps in scale between them are enormous. Going from Alpha Centauri to Sagittarius Dwarf is a leap of roughly 16,000 times. Going from Sagittarius Dwarf to Andromeda is a further leap of roughly 36 times. Nothing about any of this is a friendly hop. Every step of the ladder is a factor of 10 or more that no spacecraft has ever crossed and no human machine has ever endured. There is another way to feel the same picture. Think about how long light itself takes to make each trip. Light is the fastest thing there is. Nothing with mass, nothing carrying a human body, nothing carrying a functioning machine will ever move at light speed. And yet even light, our absolute ceiling, needs specific and important amounts of time to make each of these journeys. Light needs about 4.37 years to reach Alpha Centauri. It needs about 70,000 years to reach the center of the Sagittarius Dwarf. It needs about 163,000 years to reach the Large Magellanic Cloud. It needs about 2.5 million years to reach Andromeda. Set those durations against the age of the human species. Anatomically modern humans are, at most, a few 100,000 years old. Light travelling to Andromeda has been in flight for roughly 10 times the entire existence of our species. Light from Andromeda that reaches us tonight left before our species existed at all. Light travelling to the Large Magellanic Cloud takes about as long as our species has existed. Light travelling to the Sagittarius Dwarf takes a substantial fraction of our species' existence. And that is with light. That is with the fastest possible signal that physics allows. Anything human-built, anything carrying life, will need many times longer. Voyager 1, at 17 kilometers per second, if it were pointed at the Sagittarius Dwarf, would need on the order of 1 billion years to arrive, not 70,000, 1 billion. Because Voyager is moving at a small fraction of 1% of the speed of light, and the trip to Sagittarius scales up accordingly. 1 billion years is longer than the entire history of complex life on Earth. Multi-celled organisms have only existed for about that long. Voyager's trip to our nearest separate galaxy would consume all of that. And Voyager, remember, is our fastest interstellar spacecraft. Not our slowest. Our fastest, the one that people cite when they want to talk about the outer reaches of human capability. Compared to interstellar space, it is barely moving. Compared to intergalactic space, it might as well be standing still. This is the paradox the redrawn map exposes. The local group looks small on paper because the paper is small. In reality, the local group is one of the most stretched out neighborhoods it is possible to imagine. Its members are separated by distances that make Voyager's 50 years of flight to the edge of our own solar system look like the first breath a runner takes at the starting line of a marathon that lasts 100 million years. And the runners we can imagine building are barely any faster than Voyager. There is a particular reason this matters for the question we are asking, because earlier we allowed ourselves the possibility that the friendliest definition of nearest galaxy might rescue the question. We said, well, if the closest galaxy is the Sagittarius Dwarf or the Canis Major structure, or one of the ultra-faint satellites, at least the distances are shorter than to Andromeda. And that is true. They are shorter, but shorter in this context is not meaningful in the way it sounds. Shorter in this context is the difference between a trip that would consume 10,000 human civilizations and a trip that would consume 100,000 of them. It is a shortening from unimaginable to slightly less unimaginable. It does not turn any of these trips into something a human being could survive. There is another honest thing worth noticing on this redrawn map. The Sagittarius Dwarf's proximity is not exactly a gift, because that dwarf galaxy is being pulled apart. Its stars are trailing off into streams that wrap around the Milky Way multiple times. To even define a destination inside the Sagittarius Dwarf, you have to decide what you are aiming for. Its dying core, which will not exist in its current form for very much longer on cosmic timescales. A particular star inside it, a region of its diffuse remaining structure, the nearest galaxy, in this closest of all sense, is a moving, dissolving target. You are aiming at a place that is in the process of ceasing to be a place. The Magellanic Clouds are more stable in the short term, though even they are on complicated orbits that make their long-term future genuinely uncertain. Some modern modelling suggests the Large Magellanic Cloud may itself eventually be torn apart or absorbed by the Milky Way over the next several billion years. So even our most familiar bright satellite galaxies, the ones people can point to in the southern sky and say, "That is a galaxy near ours," are on their own long journeys that a human mission would have to somehow keep pace with. Only Andromeda offers something like a stable, coherent, unambiguous destination. And Andromeda, we have just seen, is on the far end of the redrawn map, at distances that make the closer, dissolving options look almost intimate by comparison. This is the shape of the problem. Not how far is one specific closest galaxy, but which impossible distance would you like to attempt to cross? Every candidate on the menu is a trip so long that our fastest existing spacecraft would need timescales measured in the age of species or the age of continents to complete it. And that is before we even talk about carrying a human being through the trip alive. That is before we ask what happens to a machine, or a body, or a civilization over such durations. That is before we ask whether it is even possible to shorten the trip by moving faster, and if so, at what cost. Because the natural response to everything we have just laid out is the same response people always reach for. Fine, someone says. We cannot cross 70,000 light-years at Voyager speeds. Nobody was ever seriously proposing to. What if we go faster? What if we build ships that move at a small percentage of the speed of light, or a larger percentage, or something close to the ultimate limit? Surely the trip becomes reasonable then. Surely the Sagittarius Dwarf comes within reach if we can get up to, say, 1/10 of light speed. Surely the Magellanic Clouds are only a few centuries away at those velocities. Surely Andromeda, at truly relativistic speeds, becomes a lifetime journey. That is the natural response, and it is not entirely wrong. It is just far, far more expensive than most people realize. And that is what we need to look at next. Because the moment you start asking what it would actually take to move a real object at those velocities to accelerate it, to keep it going, to protect it from what it encounters, to slow it down at the far end, so that it does not simply pass through its destination at unimaginable speed, you discover that the equations do not treat percentages of light speed as gentle numbers. The energy required does not scale linearly. The impact hazards do not scale linearly. The distances and durations do not shrink cleanly. Every apparent shortcut brings its own catastrophe. The redrawn map we have just built is only the geography. It tells you where the destinations sit and how absurd their positions are compared to anything human machines have ever managed. It does not yet tell you what happens when you try to go there. It does not yet tell you what happens to the ship, or the crew, or the civilization that launched them, when they attempt to compress 70,000 or 163,000 or 2.5 million light-years into anything resembling a human timescale. That is the next question. And it is the question where the arithmetic stops being just intimidating and starts becoming genuinely brutal. Because the map, as we have redrawn it, is only the starting condition. What follows is the physics of trying to cross it. There is an instinct that emerges here, worth taking seriously because almost everyone has it. It goes something like this. Yes, Voyager is slow. Voyager was never meant to be a starship. Voyager is a small, decades-old probe drifting outward at the pace physics allowed us to give it in the 1970s. Of course, a trip to the Sagittarius Dwarf at Voyager speeds is absurd, but surely we can do better. Surely a serious interstellar spacecraft, one designed from the ground up for the task, could move at a real fraction of the speed of light. Surely the numbers become sane once we stop using probes built for the outer planets and start imagining ships built for interstellar space. That instinct is completely reasonable, and it is completely wrong. Not because faster is impossible in principle, because the moment you ask what faster actually costs, in energy, in impact hazards, in navigation, in slowing down at the far end, the arithmetic stops being merely difficult and starts being genuinely hostile. So now we do the math. Not the friendly, hand-waved math of, well, at 1/10 of light speed it would only take a few 100,000 years. The math that respects what accelerating a real physical object actually requires. What happens to that object when it encounters real matter in real space? And what has to happen at the other end, so that the object does not simply pass through its destination too fast to see? We will start with the engines that already exist, and then we will step up the ladder of hypothetical velocities. Each rung will look better on paper. Each rung will introduce a new catastrophe underneath the paper. Let us begin with what humans have actually built. Voyager 1, as mentioned, moves at about 17 kilometers per second relative to the Sun. That is roughly 61,000 kilometers per hour. In everyday human terms, that is astonishing. In cosmic terms, it is a crawl. If Voyager were pointed directly at the center of the Sagittarius Dwarf, at approximately 70,000 light-years away, it would need on the order of 1.25 billion years to arrive. 1.25 billion years. That is more than a quarter of the entire age of the Earth. That is longer than the entire history of animals on our planet. That is the trip time for our fastest working interstellar spacecraft to reach the closest galactic destination. We have a dwarf whose stars our galaxy is already tearing away and folding into itself. Aim it at the Large Magellanic Cloud instead, at roughly 163,000 light-years, and the number becomes something close to 3 billion years. Aim it at Andromeda, at 2.5 million light-years, and you are looking at something on the order of 45 billion years, which is longer than the current age of the universe. Voyager will not be doing this trip, or any version of it. Voyager is a lesson, not a candidate. It shows us how bad the problem is at the speeds our species has actually achieved. Now consider the Parker Solar Probe. This is the fastest human-made object ever built, and it achieves that title not because it has some revolutionary engine, but because it falls repeatedly toward the Sun on carefully designed orbits, using the Sun's own gravity to accelerate. At its closest approaches, Parker moves at approximately 200 kilometers per second, over 10 times faster than Voyager. That is genuinely impressive. It is also completely dependent on the Sun. Parker is not travelling anywhere. Parker is looping. But let us pretend, generously, that we could somehow send an object at Parker's peak speed toward another galaxy. 200 kilometers per second sounds much better than 17. So how much does the trip shrink? Not enough. 200 kilometers per second is still only about 1/1500th of the speed of light. A one-way trip to the Sagittarius Dwarf at Parker's speed would take on the order of 100 million years. That is a genuine improvement on Voyager. It is also longer than the entire time since dinosaurs walked the Earth. The Large Magellanic Cloud would take on the order of 240 million years. Andromeda would take on the order of 3.75 billion years. Even at more than 10 times Voyager's velocity, we are still talking about trips that would consume geological ages. And we should be honest, that even sustaining Parker's speed all the way to another galaxy is not something the probe was designed to do. Parker only reaches those velocities near the Sun. It is not a design for interstellar cruise, but even if we grant it, the math laughs. So current spacecraft are not the answer. That was expected. The interesting question is what happens if we consider velocities proposed on paper for future starships, because now we enter territory where the numbers at first seem to work, and where the price tags, on closer inspection, get catastrophic. Let us start with 1% of the speed of light. This is a benchmark that has been floated in several serious speculative proposals, most notably in the breakthrough Starshot concept from the 2010s, which proposed pushing very small light sail probes toward Alpha Centauri at around 20% of light speed. We will get to 20% in a moment. First, 1%. 1% of the speed of light is roughly 3,000 kilometers per second, which is about 15 times faster than Parker's peak speed, and roughly 175 times faster than Voyager. At that speed, ignoring for now the small matter of how you get up to it and how you slow down again, a trip to the Sagittarius Dwarf center would take approximately 7 million years. The Large Magellanic Cloud, about 16 million years. Andromeda, about 250 million years. Notice what just happened. We move to a hypothetical velocity that is not remotely achievable with current technology, one that would require a propulsion system nobody has ever built at anything close to that scale, and we still ended up with trip times longer than the entire existence of the human species by factors of tens or hundreds or thousands. 7 million years is roughly 35 times the span of anatomically modern humans. And that is the friendly answer, the one for the closest, dying, dissolving companion galaxy. Andromeda's 250 million years at 1% light speed is longer than the time since the first mammals appeared. A civilization would have to remain functional, purposeful, and coherent across that duration. No civilization has ever managed anything remotely like it. So push higher, 10% of light speed. This is where genuinely speculative propulsion concepts start to appear in the physics literature. Fusion drives, if they can ever be made to work at spacecraft scale rather than as failed reactor experiments on the ground. Antimatter drives, if antimatter can ever be produced and stored in gram quantities rather than the vanishingly tiny amounts we currently manage. Beamed propulsion, where a spacecraft carries almost no fuel and is instead pushed from behind by a colossal laser or particle beam based in the home system. None of these has ever been demonstrated at anything close to interstellar scale, and each of them faces fundamental engineering barriers that current physics can describe, but current industry cannot overcome. But they are the concepts serious researchers use when they want to talk about 10% of light speed as a possibility rather than pure science fiction. At 10% of light speed, or roughly 30,000 kilometers per second, the Sagittarius Dwarf trip becomes about 700,000 years. The Large Magellanic Cloud, roughly 1.6 million years. Andromeda, about 25 million years. Better, much better, in the sense that these numbers are no longer measured in billions. They are only measured in hundreds of thousands, in millions, in tens of millions, which is to say, they are still trips no continuous human institution has ever attempted, and no human body has ever endured, and no human machine has ever survived. 700,000 years is more than 3 times the entire existence of our species, and this is the least demanding target on the menu, hit with a propulsion concept that requires technology nobody has built. Now push to 50% of light speed. Somewhere around here we cross into territory that is not just engineering hard, but physically punishing in ways that are not obvious from the trip time numbers alone. 50% of light speed is 150,000 kilometers per second. From the point of view of an observer left behind on Earth, a trip to the Sagittarius Dwarf takes about 140,000 years. To the Large Magellanic Cloud, about 325,000 years. To Andromeda, about 5 million years. These are still enormous numbers from Earth's frame of reference. Somewhat improved for the travellers, thanks to a small amount of time dilation, but only somewhat. At 50% of light speed, the time dilation factor is only about 1.15. The travellers experience roughly 87% of the trip time that Earth measures. It is a real effect. It is not a rescue. And then we get to the true relativistic regime, 99% of light speed or higher. Here time dilation finally begins to bite in a way that changes the story for the travellers themselves. At 99% of light speed, the time dilation factor is roughly 7. That means the crew ages roughly 7 times more slowly than the universe outside the ship. Suddenly, the Sagittarius Dwarf trip, which takes about 70,000 years from Earth's point of view at that speed, feels like only about 10,000 years to the crew. The Large Magellanic Cloud, at 163,000 Earth years, feels like about 23,000 years to the crew. Andromeda, at 2.5 million Earth years, feels like about 350,000 years to the crew. Push further, to 99.9%, and the dilation factor rises to about 22. Push to 99.99%, and it rises to about 70. In principle, at velocities arbitrarily close to light speed, the trip time as experienced by the crew can become as short as you like. In principle, a crew moving fast enough could cross to Andromeda in something like a single human lifetime as felt aboard the ship, while 2.5 million years pass outside. That last sentence is the one that people usually stop at. That is the sentence that appears in articles about relativistic travel to other galaxies, framed as if it were a solution. It is not a solution. It is a description of the far end of a physics equation, sitting on top of an energy requirement that nobody who repeats the sentence usually mentions. And it is important, right here, to be honest about what is happening. The clock aboard the ship does slow down. That is real, tested physics, verified in particle accelerators every day. The clock at home does not. So if the crew's experience time shrinks to a lifetime, the universe outside the ship still ages by the full trip time. Andromeda's crew arrives, biologically, having lived one lifetime. Earth, if it still exists in any recognizable form, has aged 2.5 million years. The two clocks disagree, and both are correct. The catch is what it costs to make those two clocks disagree that much, because the energy required to push a real, massive object to those velocities does not scale like ordinary intuition suggests. In everyday physics, kinetic energy scales with the square of velocity. Double your speed, and you need 4 times the energy. Triple your speed, and you need 9 times the energy. That is already brutal. But at velocities close to the speed of light, the relativistic version of the equation takes over, and the energy required does not simply scale with the square of velocity anymore. It scales with the difference between the ship's total energy, including its rest mass, and its rest mass alone, and that difference grows without bound as the ship approaches light speed. Getting from 99% to 99.9% of light speed does not require slightly more energy. It requires roughly 3 times more energy for the same mass. Getting from 99.9% to 99.99%, roughly another factor of 3. Every additional 9 on the velocity, another enormous multiplier on the energy budget. And the ship's mass matters catastrophically. A small probe of a few kilograms is one thing. A ship carrying a functioning human crew and everything needed to keep them alive for the trip is a different problem by many orders of magnitude. Serious estimates for accelerating even a modestly sized crewed vehicle to a substantial fraction of light speed reach energies that exceed the total annual energy consumption of the entire human species, multiplied by figures that make ordinary industrial comparisons meaningless. To put a real number on it, accelerating even a modestly sized crewed vessel, say 100,000 tons, roughly the mass of a large modern aircraft carrier, to just 10% of the speed of light, requires kinetic energy on the order of 45 million billion megajoules. That figure begins to lose meaning without comparison. Total worldwide human energy consumption across all sources, every power plant, every vehicle, every heating system on Earth combined, is currently around 600,000 billion megajoules per year, which means the kinetic energy for that single ship, ignoring all inefficiencies, would consume roughly 75 years of the entire human species' current energy production, and that is only for the acceleration. The deceleration burn at the destination requires a comparable amount of energy again, and that is only for 10% of the speed of light. Push the target velocity to 50%, and the kinetic energy for the same ship rises by roughly a factor of 30. Push to 99%, and the energy required grows by a further factor of about 40, because relativistic kinetic energy diverges as velocity approaches the ultimate limit, and these are only the raw kinetic energies. Real propulsion systems are nothing like 100% efficient at converting stored fuel into motion. Chemical rockets manage a few percent. The most optimistic fusion drive projections convert less than 1% of their fuel mass to usable kinetic energy, which means that in practice the fuel and infrastructure requirements are many times larger than the raw kinetic energy figures suggest. Producing, storing, and controllably releasing that much energy without the entire ship being destroyed by its own propulsion system is a problem that has no current solution at anything close to the required scale. And that is only for the acceleration phase. You have to do all of it again in reverse, to slow the ship down at the far end. That deceleration problem is one of the most consistently overlooked parts of every popular discussion of interstellar and intergalactic travel. It is easy to imagine an engine burning at the start of the trip. It is much harder to explain what stops the ship when it arrives. There is nothing at the destination to help you. No atmosphere to brake against. No convenient star at the right position to gravity assist against, aimed the right way. If you accelerate up to 50% of light speed on the way out, you must decelerate by 50% of light speed at the other end, and that means burning a comparable amount of energy in reverse, using onboard mass, most of which you had to carry with you from the start. Which means the ship you had to accelerate was not the modest crewed vehicle you imagined. It was the crewed vehicle plus the enormous mass of fuel needed to slow it down, which means the energy you needed at the start was much larger, because you were accelerating that additional mass too. This is why serious rocket equation-style calculations for high fraction of light speed missions produce fuel requirements that dwarf the mass of the payload by ridiculous factors. Consider what ridiculous factors actually means in practice. A fusion propulsion system, even in the most optimistic theoretical calculations, converts less than 1% of the mass of its fuel into usable kinetic energy through hydrogen fusion. That efficiency, which is orders of magnitude better than any chemical propellant, is still catastrophically low for relativistic travel. To accelerate a modestly sized crewed ship to 10% of the speed of light and then decelerate it at the far end, the total mass of fusion fuel required, even under generous assumptions, would exceed the payload by factors of tens to hundreds, which means the ship you actually have to accelerate is not the crewed vessel alone. It is tens or hundreds of times the crewed vessel's mass in raw fuel wrapped around the small living compartment at the center, which means that fuel mass itself must be accelerated to relativistic velocity using more fuel, which is why the rocket equation at these speeds and with these efficiencies tends toward requirements that break the calculation entirely. Antimatter propulsion looks better on paper, because matter and antimatter annihilating each other release essentially all of their combined mass as energy. In principle, this is the most efficient reaction physics allows. In practice, humanity has produced antimatter only in vanishingly small quantities, at costs that make it the most expensive substance ever manufactured. Total antimatter production across the entire history of physics amounts to a few billionths of a gram, produced in facilities like the Large Hadron Collider and its predecessors over decades of operation. Serious estimates for the antimatter fuel required for a single crewed relativistic mission range from tons to thousands of tons, depending on the target velocity. There is a further subtlety about beamed propulsion that the standard summary does not usually cover. The beam that pushes the sail must remain focused on it for the entire acceleration phase, which for a large crewed vessel means years of continuous pointing accuracy across distances that grow to significant fractions of a light year. Even the most tightly collimated laser beam diverges over distance. A beam that starts as a tight column at the transmitter will spread out into a widening cone as it travels, and if the spread is too large, the sail simply cannot capture enough of the beam to keep accelerating. Practical estimates for a beam capable of pushing a large sail across interstellar distances require transmitter apertures measured in tens or hundreds of kilometers, structures larger than any ever constructed by humans, held to pointing accuracy comparable to a rifle sight aimed at a target on the far side of a continent, sustained for years without interruption. A tremor in the alignment, a fault in the beam generation, an unforeseen expansion of the sail material under sustained illumination. Any one of these ends the acceleration prematurely, leaving the ship coasting toward its destination at whatever partial velocity it had reached when the beam failed. And in the most demanding versions of these proposals, the sail itself must survive being illuminated by a beam whose energy density approaches that of a small star, without vaporizing, without warping, without tearing, for the entire duration of the acceleration phase. And then there are the impacts. This is the part that turns the relativistic dream into something genuinely violent, and it applies especially to any trip that crosses interstellar space, let alone the vast reaches between galaxies. The space between stars is not empty. It is thin, but it is not empty. It contains hydrogen atoms, dust grains, occasional larger fragments, all drifting slowly through the galactic environment. At Voyager speeds, that material is negligible. At 1% of light speed, it starts to matter. At 10%, it becomes a real engineering hazard. At 50% or more, and certainly at 99%, every stray hydrogen atom the ship encounters is arriving with the kinetic energy of a fast-moving bullet from the ship's frame of reference. Every dust grain becomes something closer to a small explosion. A relativistic starship crossing interstellar or intergalactic space is not gliding through a peaceful vacuum. It is being sandblasted at every second of every day by particles arriving at nearly the speed of light. Shielding against this is a problem nobody has solved. Ideas exist. Thick radiation shields on the leading face of the ship, magnetic deflectors to push charged particles aside, sacrificial ablative layers, but every one of them adds mass, and every additional kilogram of mass makes the energy problem worse. The situation over intergalactic distances has one silver lining and several new problems. The silver lining is that intergalactic space, on average, is emptier than interstellar space within a galaxy. There are fewer atoms per cubic meter. The bad news is that the trip is far, far longer, so the total cumulative dose of high-speed impacts integrated over the whole journey is still enormous. And there are also cosmic rays, which are high-energy particles moving through space independently, arriving at the ship from all directions with their own considerable energies. Even at rest, the ship would be exposed. At relativistic speeds, the ship's motion combines with the cosmic ray energies to produce an environment that is genuinely lethal to unshielded biology and highly damaging to unshielded electronics. Navigation is another problem that grows in ways people rarely mention. At Voyager speeds, over decades, small errors in course can be corrected. At relativistic speeds, over hundreds of thousands or millions of years, tiny miscalculations in the initial trajectory compound. The target itself is moving. The Sagittarius Dwarf is being pulled apart, its center drifting on a complicated orbit around the Milky Way. The Large Magellanic Cloud is on its own long orbit. Andromeda is falling toward us at roughly 110 kilometers per second. Over the trip time, all of these destinations will have moved from where they were when you launched. You cannot aim at where they are now. You must aim at where they will be. And the further the destination and the longer the trip, the more sensitive the arrival becomes to any error in that prediction. Even if you know exactly where you are going, you still have to know exactly where you are, at every moment of a trip that lasts longer than any recorded civilization. Onboard navigation systems will have to remain accurate across durations that exceed the mean lifetime of every piece of technology humans have ever built. And communications with home for course corrections stop being useful very quickly. At Andromeda's distance, a radio signal takes 2.5 million years to reach Earth and another 2.5 million to come back. There is no help from home. There is no mission control. The ship is alone, in a way no human vehicle has ever been alone. And through all of this, we have only been discussing what it takes to move an object across the distance. We have not yet talked about what has to be alive inside that object for the trip to count as humans reaching another galaxy. Because a probe crossing to the Sagittarius Dwarf, however heroic, is not what people usually mean when they ask whether humans could ever reach another galaxy. A radio signal received in Andromeda millions of years from now is not what people mean either. What people usually mean is living humans, or something recognizably descended from them, arriving alive at the destination with the ability to walk out of the ship and stand somewhere new. That question is where all of this arithmetic meets biology and civilization. Because even in the friendliest relativistic scenario, where a crew moving at 99% of light speed experiences the trip as hundreds of thousands of years rather than millions, hundreds of thousands of years is still longer than every human civilization that has ever existed. Nobody has ever built anything meant to function continuously for that long. No power source has ever run without interruption for that long. No biological population has ever remained coherent, healthy, and reproductively viable across that duration in a closed environment. And that is the friendly answer. And that is only the friendly answer if the physics of getting up to those speeds can be paid for, which, as we have seen, requires energies that are almost impossible to describe using anything from human industrial experience, requires shielding that has never been designed, requires deceleration schemes that have never been tested, requires navigation that has never been sustained, and requires all of these problems to be solved simultaneously, not one at a time, because a failure in any one of them ends the mission. There is a temptation to declare intergalactic travel impossible. That would be dishonest. Nothing we have said proves that it is impossible in principle. The equations of physics do not forbid a sufficiently advanced civilization from building relativistic starships, at least on paper. Fusion propulsion, antimatter propulsion, and beamed propulsion are not violations of known physics. They are only violations of known engineering. What we have shown is something more specific and more uncomfortable than impossible. We have shown that every apparent shortcut carries its own catastrophe. That going faster does not simply shorten the trip. It multiplies the energy budget catastrophically. It intensifies the impact hazards. It compounds the navigation problem. It creates a deceleration problem as expensive as the acceleration problem. It does not make the journey easier. It makes the journey different, and different in ways that trade one impossible problem for another. And even in the most optimistic scenario, where every one of those engineering catastrophes is somehow solved, the crew still has to survive the trip. The ship still has to remain functional. The people inside still have to remain people, and remain the same people, in some meaningful sense, at the other end. Because the trip time, however you slice it, is not the trip time of a scientific expedition. Even reduced by time dilation to the friendliest possible number, it is a duration longer than any human enterprise has ever coherently endured. Which means the real question is not whether we can build the engine. The actual question is what has to ride inside the engine, and whether that thing can still be called a human mission by the time it arrives. That is the question waiting for us next. Because the moment you stop asking how fast the ship goes and start asking what has to remain alive and functional and purposeful inside it across the durations we have just calculated, the whole nature of the problem changes. The engine was never going to be enough. What has to survive is not just a machine. It is an entire way of being human. We left ourselves a moment ago with a strange question. Not, can we build the engine, but what has to ride inside it? Everything we have said so far is really about physics. And physics, at least in principle, is negotiable. A sufficiently advanced civilization might one day learn to accelerate a small crude vehicle to a substantial fraction of light speed. It might learn to shield that vehicle from what it encounters. It might learn to slow it down at the far end. All of that is enormously difficult, requires energies and materials nobody has ever produced, and stretches every known engineering discipline past the breaking point. But none of it violates a known law of nature. In that narrow sense, it is imaginable. The problem is that the imaginable engine is not the whole mission. The engine is only the thing that moves the ship. What has to survive the trip is not the ship. What has to survive is whatever is inside it. And when we lay out honestly what whatever is inside it would need to be across the durations we calculated earlier, we start to see that the real difficulty of reaching another galaxy is not out there in the vacuum. The real difficulty is in what has to remain functional, coherent, and recognizably human for a length of time that no human institution has ever endured. This is where we look at that, and where the meaning of the trip finally comes apart. Let us begin with the simplest thing: air. A crude spacecraft crossing to the Sagittarius Dwarf at, say, 10% of light speed needs to keep a breathable atmosphere circulating inside its hull for roughly 700,000 years. Do not skip past that number. 700,000 years. That is a duration longer than the interval separating us from the earliest members of our own genus. Older than the split between Neanderthals and modern humans by a comfortable margin, during which the ship must maintain the correct partial pressures of oxygen and nitrogen, remove the carbon dioxide the crew produces, filter out trace contaminants, prevent leaks that would kill everyone aboard, and do this without a single sustained failure across a duration that outlasts entire geological epochs. And that is on the friendly definition of the drip, aimed at the friendliest destination, with a propulsion technology nobody has ever built. Water and food and waste are the same problem in different forms. A ship on a trip of that length cannot be resupplied. It cannot carry water for the trip. It cannot carry food for the trip. It cannot even carry the raw feedstock for the food for the trip, because the mass required over hundreds of thousands or millions of years is preposterous. The ship must instead operate as a closed, recycling ecosystem, Water must be recovered from every biological process and purified and reused indefinitely. Nutrients must be cycled from waste back into food production through some combination of biological and chemical processes. Every element of the crew's diet must be regrown, refarmed, refished, or refabricated on board. And every one of those cycles must run continuously, without a permanent breakdown for the entire duration of the journey. We have never built a closed ecosystem that works. The most famous serious attempt, the Biosphere 2 experiment in the early 1990s, aimed to sustain a small crew inside a sealed environment for 2 years and encountered severe problems within months. Oxygen levels dropped in ways nobody had predicted. Certain species collapsed, others exploded in numbers. The chemistry of the enclosed atmosphere drifted. The system did not fail spectacularly, but it did not succeed either. It required continuous outside intervention to remain viable. That was 2 years, on Earth, with a full support team standing by, in an environment we had built specifically to study exactly this problem. The trip we are describing needs closed ecosystems that work not for 2 years, but for hundreds of thousands of years. Without outside intervention, without a support team, without a planet's worth of buffer chemistry to lean on, that is not a scaled-up version of Biosphere 2. That is a different category of problem. Now add the humans. A crewed intergalactic mission cannot be crewed by the same humans from launch to arrival. Even the friendliest relativistic scenario, where time dilation reduces the crew's experience time to tens of thousands of years, still requires many generations of crew inside the ship. Hundreds of generations. Perhaps thousands, depending on the target and the velocity. That means the mission is not a mission in the conventional sense. It is a multi-generational voyage. The people who launch it will not be the people who arrive. The people who arrive will not have known the people who launched. Every generation aboard the ship will live and die entirely within the ship, having never seen the destination and having only known the origin through records, which raises the question of genetic viability. A closed human population aboard a spacecraft is subject to all the constraints that geneticists have identified for any small, isolated population. Inbreeding depression becomes a real risk if the founding population is too small. Loss of genetic diversity through drift becomes real over long timescales. Estimates for the minimum viable founding population for a long-term human generation ship vary considerably in the literature, from a few dozen with heavy management to a few hundred with careful reproductive planning, to several thousand for a more forgiving margin. All of those estimates assume that the population is actively managed, that reproduction is monitored and organized across generations, that certain kinds of pairings are encouraged and others avoided. In other words, the crew is not free in the way people on Earth are free. Their reproductive lives are subject to the constraints of the ship's survival, and even a well-managed population will drift. Over hundreds of generations, the humans on the ship will diverge, biologically and culturally, from the humans on Earth. Not because of anything dramatic, simply because that is what closed populations do over long timescales. The people arriving at the destination will be genetically and culturally distinct from the people who launched them, in ways that will only grow larger the longer the trip lasts. Now consider the machinery. Every ship system, every reactor, every recycler, every pump, every seal, every processor must either continue to function for the duration of the trip, or must be repaired and replaced by the crew themselves. Nothing lasts hundreds of thousands of years without maintenance. Nothing we build lasts even hundreds of years without maintenance, which means the ship must carry, or must be able to manufacture, replacement parts for every one of its components. And it must carry, or be able to manufacture, the tools needed to manufacture those parts. And it must carry the knowledge, distributed across every generation of crew, of how to make the tools that make the parts. That last point is quietly one of the hardest, because human knowledge is not stored in books, it is stored in people. The skill of a machinist is not the words in a manual, it is the practiced understanding of what a piece of metal does under a lathe, learned by doing, transferred by working alongside somebody who already knows. The skill of a farmer, an electrician, a doctor, a chemist, a nurse, an engineer, is not a text file. It is a lived apprenticeship, and every one of those skills has to be transmitted, faithfully and continuously, across every generation aboard the ship. for the entire duration of the trip. If a skill is lost, even temporarily, the systems it supports will fail, and if enough systems fail at once, the ship dies. That is a civilisational problem, not an engineering one. It is not solved by building the ship better. It is solved, if at all, by ensuring the humans aboard keep teaching each other everything they need to know across hundreds of generations, without a single generation dropping the thread. No human civilization has ever done this. Every civilization that has ever existed on Earth has lost knowledge, sometimes catastrophically. Techniques for building certain kinds of arches, mixing certain kinds of cements, casting certain kinds of bronze, have all been lost and later rediscovered, sometimes only partially, and those civilizations existed in the far more forgiving context of an entire planet, with agriculture, with children learning skills their parents never used, with the freedom to fail in one region and recover from another. The ship has no other region. If knowledge is lost aboard the ship, there is nowhere else it can be relearned from, and there is the reason to keep going. A generation ship is not just a technical challenge, it is a cultural one. Every generation aboard, from the second onward, is being asked to spend its entire life inside a machine, maintaining the machine, so that a distant generation none of them will meet can arrive at a destination none of them will see. That is a particular kind of ask, and it has to be renewed, generation after generation, without loss of commitment. The people aboard the ship must continue to believe that the mission is worth their labour, worth their reproductive choices, worth the constraints on their lives, worth teaching their children the same way, forever, until arrival. Human beings have held purposes for a lifetime, occasionally across a few generations, and never for the durations we are describing here. Empires have fallen inside centuries. Religions have transformed inside millennia. Languages themselves become unrecognizable across a few thousand years. On the timescales we are discussing, the very language that the crew speaks will drift into something new. The stories they tell about why they are aboard the ship will drift. The stories will change, will be revised, will possibly be forgotten and rewritten. Whether the ship's purpose survives this drift is not a technical question. It is a question about whether any human population can hold a single long-term goal across durations longer than any civilization has ever held anything. Now let us fold in the time dilation, because in the more optimistic, relativistic scenarios, the crew's experienced time can be much shorter than the trip time in Earth's frame. At 99% of light speed, as we noted earlier, a 2.5 million year trip to Andromeda is felt as about 350,000 years by the crew, pushed to 99.99%, and the crew's experience time drops to something in the tens of thousands of years. In principle, at velocities arbitrarily close to light speed, the crew's experience time can be reduced further still. That does not eliminate the problems above, it only compresses them. Tens of thousands of years is still longer than every recorded civilization. Even the most heavily time-dilated version of this trip still asks a closed human population to remain coherent, healthy, culturally continuous, and purposeful across a duration nobody has ever managed. And this is where the second half of relativistic time dilation becomes important, and it is the half that popular treatments almost always leave out. The clock aboard the ship slows. The clock outside the ship does not, which means the crew's experience time is not the trip time. The universe's experience time is. If the crew feels one lifetime pass, and Andromeda's arrival takes 2.5 million years in the frame of anyone left on Earth, then 2.5 million years have actually passed on Earth. Not for the crew. For everyone else, the civilization that launched the ship, if it still exists, is 2.5 million years older than the version that said goodbye, which is a way of saying that it is almost certainly not the same civilization at all. 2.5 million years is comparable to the entire span of the genus Homo, from its earliest known members, longer than the span of any single human species, longer, in fact, than most mammalian species survive at all. So even in the most generous relativistic case, the ship arrives at Andromeda, and the crew, having lived their compressed lives, steps out onto a world in a galaxy the size of ours, having severed every practical connection with the civilization that built them. Earth, if it still has an Earth, is 2.5 million years further along its own history than when the ship left. Any message from the crew announcing safe arrival will take another 2.5 million years to travel back and be received, if there is anyone left to receive it. Any reply will take 2.5 million years more to reach the ship. Communication with home is not merely delayed, it is functionally impossible. The crew is not on an expedition. There is no ground control they are reporting to. There is nowhere they can return to. As Browned. The stop, there is nothing they can meaningfully send home, which brings us to the heart of what this whole episode has been circling. If the crew has severed every practical connection with the civilization that launched them, in what sense is the mission still from Earth? In what sense are the people aboard still emissaries of the species that sent them? They carry Earth's biology, in some altered and drifted form. They carry Earth's records, in whatever form has survived hundreds of thousands of years of storage and transmission. They carry perhaps some memory that they came from somewhere else, but they do not share Earth's present. They do not share Earth's society. They do not share Earth's lived history. They are, functionally, a new human civilization, launched permanently away from the parent, arriving at a destination it has become its own reason for existing. This is the transformation the trip performs, and it is the reason the phrase, reaching another galaxy, quietly changes its meaning as we look closely at it. Reaching another star is a long trip, but it is imaginable as an expedition. A crew leaves, a crew arrives, and even if the trip lasts centuries, there is some meaningful connection between departure and arrival. Reaching another galaxy is different. Reaching another galaxy, at any velocity physics currently permits us to imagine, is a trip that outlasts the practical continuity of any human civilization. The people who arrive have not gone anywhere on behalf of Earth. They have become something else and taken it somewhere else. The mission has not so much reached another galaxy as it has grown a second civilization and set it down light years away. And this reframing matters because of what it means about the original question we set out with. The question was whether the closest galaxy might be too far for humans. We have been building the answer, piece by piece. First we saw that the closest galaxy is not one number, but a definitional choice, and that even the friendliest choice, a half-dissolving dwarf orbiting inside our halo, is far. Then we saw that far, at galactic scales, is not what far means in ordinary experience. It is thousands or millions of times further than the nearest star, which is already unreachable at current speeds. Then we saw that going faster does not solve the trip, because every increment in velocity costs enormously more energy, introduces new impact hazards, and creates a symmetrical problem of deceleration that most enthusiasts quietly forget. And now, finally, we see that even if all of those physical problems are somehow overcome, the trip still requires the ship to become a world, and the crew to become their own civilization, and the connection to the origin to be functionally lost, which means the phrase, too far for humans, has to be understood carefully. Nothing in what we have said proves that no object could ever cross to another galaxy. Nothing here shows that a probe, or a signal, or a self-repairing autonomous system could not in principle be sent across the gap. There is no wall of physics that forbids matter and information from making the crossing, given enough time and enough energy. That is not the constraint. The constraint is that humans, in the ordinary meaning of the word, cannot make the crossing without ceasing to be humans in the ordinary meaning of the word. The trip transforms the crew. It transforms the mission. It transforms the connection to Earth. And it does all of this before the ship even arrives, because the timescales themselves force the transformation. There is a quiet way to say this and a loud way to say this. The quiet way is that reaching another galaxy is not a technological problem but a civilisational one. The loud way is that reaching another galaxy would require humanity to launch, not a spacecraft, but a smaller version of itself, permanently, into a journey longer than its own history, in the hope that whatever eventually stepped out of the ship at the far end would still recognise itself as the descendant of the people who built it. Whether the loud way and the quiet way are describing the same thing, or slightly different things, is a question we can each sit with for a while. What they share is the recognition that the difficulty is not really located in the engine, or the shielding, or the recyclers, or the reactor. The difficulty is located in what has to remain a continuous human enterprise across a length of time no continuous human enterprise has ever endured. And there is something else worth noticing about this framing, because it changes the emotional shape of the answer. When people say that another galaxy is unreachable, they usually mean it in the language of impossibility. They mean that the numbers are too big, the energies too vast, the distances too extreme. That framing is not wrong, but it does treat the problem as if the universe were closing a door in our faces. There is a different framing available, which is that the universe is not closing any door. It is only telling us that the door is on the other side of an enormous room, and to walk across the room we would have to become the kind of thing that can walk across it. A species that has learned to build ships that are worlds. A civilization that has learned to distribute its purpose across durations longer than its own history. A biology that has learned to remain viable across generations counted in the hundreds or thousands, in an environment that provides nothing except what has been built into it. Whether that is impossible depends on what impossible means. It is certainly beyond us now. It may be beyond us always. It is not necessarily beyond every possible descendant of us. But even if some far future descendants of humanity manage such a thing, the mission they launch will not really be a mission home to their parent civilization. It will be a colony, in the deepest sense of the word, a separation, a permanent one, an act of setting one part of humanity down in a place none of the rest will ever see or hear from again. And this, finally, is the meaning of the distance. The gap between our galaxy and any other is not a distance that a mission crosses. It is a distance that a mission becomes. The people who go do not carry Earth to another galaxy. They become something else on the way and land there as themselves. There is a strange dignity in that idea, and there is also a strange grief. Dignity, because it means the universe is not simply refusing us. It is asking a real question about what we would be willing to become in order to answer it. Grief, because it means that any success would also be a kind of loss. The humans who arrive at Andromeda, or the Large Magellanic Cloud, or the drifting remains of the Sagittarius Dwarf, would carry Earth's ancestry in a way that a distant descendant carries the ancestry of a great-great-great-grandparent. They would know they came from somewhere. They would not know that somewhere in any lived sense. Earth would be a name in their records, a story in their traditions, a set of chemical signatures in their bodies, not a home, not a place they could go back to, not even a place they could imagine going back to, because the very idea of going back would have stopped being a coherent idea 100 generations before they arrived. And so the nearest galaxy is too far for humans in a specific and precise sense. Not too far for objects, not too far for information, not too far for very careful autonomous systems that might, one day, be able to cross the gap and record something on the other side. Too far for humans in the sense that a human going would not be the same human arriving, and a civilization launching such a mission would not be the same civilization receiving news of its success. The trip is too long for a person to survive as themselves. It is too long for a civilization to remain itself across. It is too long for the meaning of arriving to survive intact, which is why, in the end, the closest galaxy is not close. Not because of a number of light years, though the numbers are formidable. Not because of an unpayable energy bill, though the energies are staggering. But because of what would have to change on the way. Distance, at galactic scales, is not really distance. It is a length of time that transforms whatever is trying to cross it. And humans, however far our engineering may one day reach, are made of the kind of continuity that does not survive being stretched that far. So when someone asks whether we will ever reach another galaxy, the honest answer is not yes and not no. The honest answer is that reaching another galaxy would require humanity to become something else before it arrived. Something that could hold a purpose across durations longer than any of our institutions. Something that could remain coherent across generations counted in the thousands. Something that could keep repairing itself, feeding itself, and teaching itself for spans of time longer than the age of our species. Whatever eventually did such a thing might carry our name. It might carry our chemistry. It might carry the distant memory of the world we launched it from. But it would be its own thing. It would have earned another galaxy by ceasing to be quite what we are now. Perhaps that is what the closest galaxy is really asking of us. Not a faster engine, not a bigger reactor, not a better shield, but a version of ourselves patient enough and continuous enough and transformed enough to become the kind of traveller such a distance requires. Whether we will ever be that, or whether any species ever is a question the universe leaves entirely open. What it does not leave open is the price of the ticket. The nearest galaxy is close only on paper. In the currency that matters in bodies, in generations, in civilizations, it is a distance so long that whatever pays it will not, at the end, be the thing that started walking. And that, perhaps, is the deepest way to answer the question we began with. The closest galaxy may be too far for humans, not because it lies beyond a wall, but because reaching it would require humanity itself to cross a threshold on the way. The nearest galaxy is not on the far side of a distance. It is on the far side of who we would have to become to arrive.